Thank you all for coming. I will continue. So today I will talk about pseudo-differential operators and connections with groupoids. Before I start, I just wanted to mention an example because everything we are doing depends on some vector fields which satisfy Hörman's condition. So one might get the impression that if my vector fields depend on some parameter continuously, then everything we are doing also depends on this parameter continuously. This is false. Right. So okay, so you can get very different behavior once everything we are doing doesn't depend on these vector fields in a continuous way. So let me recall the properties we had from before. So we had some algebra. So I want to erase this. Don't need it anymore. So we had a space for every k in R. We had a space inside endomorphisms C infinity functions. Half densities which satisfy the properties. It's an algebra. I'll just write psycho. And this property tells me that I can extend elements here to endomorphisms of C minus infinity, because I could just say P of U applied to F is piece it's also true with the transpose. And so I can define this as P transpose of U of P transpose of F. The second property is that I have a symbol. So for every P here, and for every X in M and pi in this set of representations, I have some map of P, X, and pi inside, which is an endomorphism of infinity vectors. And this is algebraic, so the symbol of P, I wrote without key. So the symbol of P, Q, X pi is the symbol of P. And the other is the symbol of P star, is inside the symbol of P, X bar star. And the third is that if D is a differential operator of order K, then D is in psi K, and the symbol is the symbol. The symbol, this here, is the symbol that we had from before. And the fourth property is that if P is pseudo of order 0, then P is bounded. And if P is pseudo of order negative, then P is compact. So all of these are the same properties shared with classical.
I cannot read the third line. If D belongs to what?
If D is a differential operator of order of Hörmann order K,
okay.
then it's also a pseudo differential. Okay. So all of these are exactly the same as the classical calculus, and then the new properties which differ slightly from the calculus, from the classical calculus, is these three properties. So phi prime, if P is in psi k such that for all x in M and pi in 2x except the identity, this thing is injective, then I can find Q in psi minus k such that QP minus the identity, the symbol of this vanishes. Sometimes I put k to signify that this is of order k, but I didn't do it last time, so I will not do it this time. So this tells me that I can, maybe I cannot find the parametrics, but at least I can find the parametrics at the level of the principal symbol. So I can find something which makes the principal symbol vanish. The second is that I can actually find some operators which have parametrics. For every k in R, I can find an operator of order k such that this operator has a two-sided parametrics. Huh? You can take Q to be P minus K.
The product PK, PL?
Yes, you can take them so that you can take them in addition so that PK, PL is PK plus L modulo regularizing operators, if you want. And of course, PK star is PK. But for the proof that I will give in a moment, this is suffice. I do kind of need that if k is an integer, then I can choose this pk to be a differential operator. If k is not if k is a power of is an even natural number.
Big enough?
No, just if k is in 2n, then I can actually take this one. The Hallman sum of squares taken to the power k over 2. Yes. Yeah, I should learn how to. And the third property is that if P is an operator of order 0 and its symbol vanishes, then for all x in M and pi in 2x, then this is compact. Okay? Now, using these properties, I will give a very short proof of the main theorem, which explains why all of these properties suffice for our purposes. Now, I will remark that, so we define a calculus in our joint work with Andrew-Lattakis and Juncken, but many people have defined calculi of this sort before in various degrees of generalities. So, for example, Brian Street has a book in Annals of Mathematical Studies from 2008 or 9, or even 6, which defines such a calculus. But the main point, the main new thing in our work is that usually there is no principal symbol. So people define some calculus, but they don't define a principal symbol map. So they don't have 2. They have 3 and 4. And they even have 4. Here I used L2, but they have 4 with LP. P between 1 and infinity excluded both sides. But they don't have this. So it's the principal symbol and these properties which is new. They have this one. This one is easy. This one is very old. The fact that there are some operators which have parametrics, these ones they have. Okay? It's these two and the principal symbol, which is really the new thing in our way of defining pseudo-differential operators. Okay? So I will keep these because these are the ones which are interesting, and I will erase this and I will prove. So I will state the theorem. So, what is this? This is a further key. What is the question?
No, I can't understand. 5 seconds means there exists an operator which has
yes.
right and left
Parametrics. And I say that if k is in 2n, then yes. The Harman are some squares.
No, it's strange that you just say there exists something that has.
I mean, okay, so so you will see why I need it in a moment. So I'll define the subgroup of spaces. I define the subgroup of spaces for k in n. Now I can define them in k in R to be the set of all u in C minus infinity of M, such that for all p in H in psi, k, p of u is in L2. And the point is that this thing is a priori, so I can always put on it a locally convex topology by just taking a family of semi-norms given by all of these operators. But the point is that it's a Hilbert space because I can choose, it suffices to know that this is satisfied for these operators. So 5, the second 5, this implies that this thing is a Hilbert space. If M is compact, so I'm supposing that M is compact here. And what I want to say by this is that if K is natural number, then it coincides with the subgroup of space that we defined from before. So this is the only part where that's not the only part. Okay, now I can state, so what we will prove is the following. So theorem, if, it's if and only if, but so I start with any pseudo-differential operator, if for all x in M and pi in tau x with 1 removed, this thing is injective, and the other, so I have this and I have for all s in R, for all u in C minus infinity, pu is in Hs, implies that u is in Hs plus k. And I put tilde. So here I will prove, so the theorem is that 1 is equivalent to 2, and it's also equivalent to the third for all s in R, p left invertible modulo compact. So those are all equivalent. It's also true, it's also true that in 2 and 3, here you have for all. You could also put there exists. If you know that any of these conditions is satisfied for one S, it's also satisfied for all of them, and it's principal. Now, the property which I care about, let's say, is 1 implies 2. So this is the only one which I will prove. I will pass through 3 more or less, but so we will prove 1 implies 2. And we'll see that the proof is very short, and it explains why all of these things come together. So let P here, which satisfies this condition. So by this property, I know that I can find the parametrics at least modulo the symbol. So I know that there exists Q so I write the symbol vanishes to mean that it vanishes at every point, every representation. So now it suffices to prove that this operator has this property with order 0. Because if I prove that, so if I have a distribution such that PU is in HS, then QPU is in L2. And so it suffices to show that QP has, so it suffices to show this. For all S in R. Huh? If P of U is in HS, then Q of this is in HS plus K, and so U is in HS plus K. So you just need to show this. Because by construction, if P is in psi K, then P defines an operator from HS plus K to HS for all S and R. That's precisely how we defined the Sobolev spaces. Okay? So I just need to prove this operator. So far, so good? Okay, now, so here is the trick. So I write QP is equal to QP minus the identity plus identity. It's brilliant identity, which is 2. So now the point is that this operator, QP minus identity, its symbol vanishes. So I know that it's compact operator. So QP minus identity here it will be important to be careful is compact between which spaces. So here it's compact from L2 to L2. Okay. Now, since it is compact, I can approximate it by regularizing operators. And so I can approximate this with some operator of the form R plus the identity, where R is regularizing. What I want to say, okay. What I want to say is that there exists R, which is regularizing. Regularizing means that R maps C minus infinity to C infinity, which is actually silly since I already used it, but such that QP, which is this thing, plus R is invertible. So the idea here is that when I add R, I add R to this compact operator. So I can choose R so that the norm of this is as small as I want. So in particular, I can choose it to be of norm less than 1. And so this is something of norm less than 1 plus identity, so it's invertible. Invertible, again, it's important here to be careful. Invertible from L2 to L2. Okay? I will erase this part. Now claim. So this operator is invertible on L2. Now I claim that it's actually invertible on all Sobolev spaces, not just L2. So claim for every S in R, QP plus R from HS to HS. So it maps HS to HS because it's an operator of order 0 plus some regularizing, so it's again an operator of order 0. So from HS, this is invertible. So why is this? Before I prove the claim, it's clear this finishes everything. Because R is regularizing. So adding R in this statement changes nothing. And now I prove that this map, QP plus R, it maps distributions to distributions. I prove that at each level of Sobolev spaces, it's bijective. So it preserves the levels. It's bijective from all of distributions to all distributions. So this implies, in particular, QP plus R from C minus infinity to C minus infinity is bijective. Because C minus infinity is the union of all of these Sobolev spaces. So I prove that it's bijective on Sobolev spaces, on all distributions, and it preserves the level of Sobolev spaces. So I get this. It's bijective from C minus infinity to C minus infinity, and also from C infinity to C infinity. It's bijective in all situations. This would follow from the claim, from the Sobolev space. So I will erase this. I can erase this. So now, how do we prove that this is invertible from HS to HS? So the first thing to notice is that this thing is actually Fredholm of index 0. Why it's Fredholm of index 0? Because it's an operator from HS to HS. I want to look at it as an operator from L2 to L2. And so I take these operators that I had, pk, which gave me this isomorphism from HK to L2. And so if I want to see this as an operator on L2, I could just multiply QP plus R, and I multiply with P minus K, and I multiply with PK. So now this operator is an operator from L2 to L2, and it's conjugate to this.
I guess it's enough to take K big enough so you could take K to be an even integer.
Here I said K, it's S. Yes, yes, you could do tricks of this sort. You don't need to do it for every S. For S big enough, you can do something like this. So now the trick is that this operator is the identity. The symbol of this operator was the identity. And so the symbol of this operator, because those things cancel each other, the symbol of this is also the identity. If you want, the symbol is the identity.
Because the regularizing part doesn't see.
Yes. So the regularizing part doesn't see, it has symbol 0, and QP has symbol the identity. And here I use PS, but I could have used the regularizing for PS. So here Q is regularizing for PS. Yes, for PS. It also works with P minus S if I chose the PS to be those which have the property that PK plus L is PK times PL. But I don't need that. Because it's regularizing, the symbol of this is the inverse of the symbol of this. And so if I compute the symbol, I get the symbol of this times the identity times the symbol of this, so I get the identity. So this thing has symbol which is the identity. But because it has a symbol which is the identity, that means that it's the identity plus something which has symbol 0. And something which has symbol 0 is compact. So it's the identity plus a compact operator, and the identity plus a compact operator is always Fredholm of index 0. So this is Fredholm of index 0. So it's a very simple argument. We just conjugate to L2, and we just compute the symbol. So it's just a statement from before, but conjugated to L2. Now we are done, because, so what do I have? So I need two parts. So if S is positive, then I argue as follows. Then I argue that H tilde of S is included in L2. And so my operator is injected, it's invertible on L2. So it's injective on L2. So it's also injective on HS. So it's an injective operator whose Fredholm index vanishes. And so it's also surjective. And so this is QP plus R is injective on L2. So on HS, so it is bijective. Because an operator, an injective operator whose Fredholm index vanishes, is invertible. Now if S is negative, you do the exact same argument, but the other way around. So you argue that L2 is now in H tilde S, and the operator was surjective on L2. And so this operator, its L2 is included in HS, so its image will contain at least the image of L2, which was already all of L2. So the image of QP plus R will contain at least L2. But L2 is dense in HS, and so it's now a Fredholm operator of index 0 whose image is dense. And so it's also invertible. So QP plus R is invertible. And so we are done. So I remark that this is really not a conventional trick to prove, not at all conventional trick to prove that an operator is hypoelliptic of any sort. For example, we were stuck on this for 6 months. We could prove all of these properties, F5 prime, double prime, and 3 prime, but we couldn't do this trick. It's very unusual to use the Fredholm index to prove that the solution of your differential equations are C infinity. Usually you go the other way around. You first know that they are C infinity. If you look at Atiyah Singer, you first know that they are C infinity because you actually can construct a parametrics. And then you try to compute the analytic index using topological formulas and things like this. So here we use the Fredholm index to prove that the solutions are C infinity. You have a question?
Yeah, why do you want to prove that 2p plus r goes from C minus infinity? It's bijective there.
Why?
The last two lines, why do you need that?
I didn't need this. I mean,
you need the last one to show that it is hypoelliptic. You know that the inverse is
no, but he only wants to prove 2.
I want to prove 2. 2 implies hypoelliptic because if PU is.
But why do you want to prove
I don't need this, but it's a trivial consequence.
Okay.
What I'm saying is that it's bijective with all subgroup spaces. It's bijective.
Yeah, I agree, but you didn't use that.
No, I only use this one. And I also use this one as an obvious corollary. Because U here is a distribution. So I need to say that it belongs to one of these subgroup spaces. You see what I mean? I prove that it's bijective on each subgroup space. So I need that it's injective here. Because you could start with something like, so here you know that this is in HS. Yes. So you take its inverse, because it's bijective on HS. Yes. And so you know that the inverse is in HS, but you want to say that the inverse is U, not some other distribution.
Okay.
So I need that it's bijective on all distributions. That's bijective on all C infinity functions is also a trivial corollary, which would give me hypoellipticity. And here is where I use that M is compact. This is really the only place where I really needed that M is compact, because I'm computing Fredholm index everywhere. Okay? So now, how do we define these pseudo-differential operators? So we use groupoids. So as I said, one can technically define these pseudo-differential operators without using groupoids. And as I said, Street, for example, going back to Rothschild and Stein in the 70s, technically one can do this without using groupoids. The advantage of using groupoids is that you have an immediate connection with the principal symbol, and so you can prove that the principal symbol is well defined, and these three properties that we needed on the symbol. So the necessary inequalities that you need come for free from the fact that your approach uses groupoids. So the rest of this 1 hour and a half is just an introduction to groupoids. So at least it's much easier for you. So I need a groupoid is a small category where every arrow or morphism is invertible. Now, I am very much well aware that the notation we use in non-commutative geometry is not the usual notation people use for categories. It's slightly confusing. At least I was told this. So what is the notation that I'm using? So G is set of arrows. G0 is set of objects. Now, since every arrow has a source and range, so I have two maps, S and R, source and range, which go from G to G0. Usually we put this, but I'm lazy and I will forget. So might as well start forgetting now. So I have S and R, and since every arrow is invertible, I have an inverse map from G to G. Every arrow is invertible. And I have a multiplication map because it is a category. And so I have, so if I denote G2 to be the set of gamma and gamma prime, so that S of gamma is equal to R of gamma prime, then I have a multiplication map from G2 to G, which is sent to the composition. I compose them like functions. So this is it. And then a ligopoid, the other definition I need, a ligopoid is a groupoid so a ligopoid is a groupoid where this thing is a smooth manifold. So G is a smooth manifold. G0, I can identify the set of objects with the identity. So I can think of G0 as G, as a subset of G, by the identity inclusion. And so this is a closed submanifold. Actually, closed is automatic from the hypothesis. And what I also need is that all of these things are smooth, and that S and R are submersions. This thing is a diffeomorphism. If I ask that it's smooth, then because it's O in inverse, it's automatically a diffeomorphism. So I will just write it. And the last thing is that because S and R are submersions, this thing is also a smooth manifold, if I think of it as a subset of G cross G. And so I ask that this map is also smooth. And I ask that M is smooth. And again, it would follow automatically from the hypothesis that if it's smooth, it's automatically a submersion.
It's automatically
a submersion. M is a submersion because you have an obvious section which is just using the identity morphisms. So, and here, for example, I didn't need to ask that both maps to be a submersion. If I know that one is a submersion and I know that this is a smooth, then the other is also a submersion. So the minimal conditions would be asking that S is a submersion and this is a smooth and M is smooth. Anyway, so examples. So I could spend an hour giving examples. I won't do this, but I'll give the examples which are actually useful for what I'm trying to do. So the first example is a silly example, which is G is equal to G0 is equal to M as smooth manifold. So this is a trivial groupoid. There are no arrows other than the identity arrows. And so all of these maps are the identity maps. That's trivial. The other example, also kind of trivial, is G, trivial but important for us, is M cross M, and G0 is M. So one should think of it as a category. This means that the space of objects is M, and for every two objects, there is a unique arrow going from X and Y. And so S of X and Y is Y, R of X and Y is X, the inverse of X and Y is Y and X, and the product of X and Y and Z is X and Z. Okay? And this explains the motivation for us, because in a moment we'll define convolution, and this is what we use to define convolution for kernels on L2 maps. Now, third example, more interesting, slightly more interesting. So if G0 is a point, then G is a Lie group. So G a Lie group. So a Lie group is just a Lie groupoid with the G0 is identity. The last one, which is easy. After this, I will give you an interesting one. But, so the last one is if I have a family of groups, so if I have G, so for example, a vector bundle would be. In this case, the source and the range map, so if this is a vector bundle, then the source and the range is equal to pi, and the product is the addition. So E So G0, so here G0 is M, and G is E. And the source is equal to the range, the multiplication is addition, and the inverse is minus. Now, here is why I really want to use groupoids. So, to explain the motivation. So, before we had G, which was a free nilpotent Lie group, and we had this tau of X, which was a set of representations of G hat. And my problem was that I needed to look at representations of G on L2 of G over H. We started, let's say we started with our original Helfer and Noriga's construction of this cone, and then using Kirillov's orbit method, we reduced it to the representations which are weakly contained in these representations. So more or less, I'm looking at these quotients, okay, H. And H here was some element in Gx0, which was some set of subgroups, so a set of cones, which I can obtain. Now, the point is that H here is not normal. And so this G over H is a homogeneous space. Now, we all learn that when you have a group and you take a quotient, the quotient by a subgroup, the quotient is a group if and only if the subgroup is normal. The advantage of groupoids is that I can always take the quotient, and I can always take group, I always get a groupoid, and this is precisely the construction that I need. So what I need is the following. So I will construct, I will give the algebraic construction, and then I will explain what happens if I want to make it a Lie groupoid. Okay? So I take G group, any group. And I take S a subset of subgroups of G. It's the same motivation which we had here. Gx0 is a set of subgroups. So here S is a subgroup which has this property. If G is in G and H is in S, then G, H, G inverse is also in S. So for example, you could start with any subgroup and you take all of its conjugates. So S would be a point if the subgroup is normal. Then I can define a groupoid, G, which I call it the quotient of G by S. So it has both a set of arrows and a space of objects. So the space of objects for me is S itself. And the space of arrows is all of the cosets of S, left or right. So it's a set of all GH, where G is in G, H is in S. It's also the same thing as a set of all HG, where G is in G and H is in S. And it's the same thing as the set of all G, H, G prime, where G and G prime are in G and H is in S. Why? Because if I have GH, so this is a left coset, but I can write it as a right coset by saying that it's GH, G inverse. So that's now an element in S multiplied by G. So a left coset of an element in S is again a right coset, but now of another element in S. So these two sets are the same. And GH, G minus 1, I could either write it as GH, G minus 1, G, G prime. So this is a right coset. Or I can write it as a left coset by saying it's G, G prime minus 1, H, G prime. And so now it's a left coset. So all of these things, so these things are these things and these things, they give you in the same set. So now so what is the source map of, say, GH? It's H itself. And what is the range map of GH? It is the other way, which is GH, G minus 1. Okay? If you want a very simple way to write this is that the source, if you think of the coset as a subset of your group, then the source is A minus 1A, and the range is AA minus 1. If you have a coset and you multiply G as, because you will have GH minus 1 GH, it will be H, G minus 1 GH. So it's just H. Okay? And the range is the other way around. Now the inverse of GH is just the inverse as a set. So it's H, G minus 1. Now this is a right coset, which is here. I could also write it as a left coset by saying that it's G minus 1, G, H, G minus 1. If I really want to write things as a left coset. So these are the inverse. Now the multiplication. If you write them as subsets, then it's very simple. The multiplication of a coset and another is just AB. And of course, if you multiply two cosets, it's almost never a coset. But the fact that S of this is R of this forces this to be a coset. So we can check this. So A will be GH, and B will be G prime H prime. My condition is that S of A is equal to R of B. S of A, what is this? This is H. And R of B, this is G prime H prime G prime minus 1. So now I can multiply them. So I have GH multiplied with G prime H prime, but then my H is this. And so this is G prime H prime G prime minus 1 G prime H prime. So these things cancel. So you get G prime H prime H prime. And then because H prime is a group, subgroup, this product is again H prime. And so you get G prime H prime. All what you care about is that it's a coset. So it's again an element there. And of course it's associative because the product of subsets is associative. The group itself is associative. It has an inverse, so the inverse would be this. And the identity is just the subgroup itself. So the identity arrow is just the subgroup. And it satisfies all of the properties of a groupoid. It's not a Lie groupoid. If I want to make it a Lie groupoid, I have to put some topology on S to make it a groupoid, because then I want S to be a manifold. And so if I want to make it a Lie groupoid, then S would have to have a topology. In my case, S was a set of came from some subset of the Grassmannian manifold. And so I will equip S, in my case, with the topology, the subspace topology from the Grassmannian manifold. Okay? Now, a smaller problem will appear that S is not really a manifold. I will do the theory with Lie groupoids, but one would have to extend it slightly to allow groupoids where the space of objects is a subset, closed subset of a smooth manifold, but the fibers are always smooth. So this means that S minus 1 of X, let's say this set, in this case, in my case, so S minus 1 of, say, a sub H, this is G over H. In this case, the things which have which map by S to H are GH. So it's just the homogeneous space. So essentially, this groupoid puts all of the homogeneous spaces together and gives me a product structure not on one homogeneous space, but on all of them. So it's some. So this is why I call it the quotient of G by S, because it really captures the idea, the exact same idea of taking the quotient by a subgroup. But here it's a subgroup. It's a groupoid. So I will not use this today, very probably, but it will be used tomorrow, next week. But anyway, the whole reason why I really need groupoids is why groupoids are useful here is because of all of this. So now I need a few things which are exactly the same as one does in for Lie groups. So if X, so here now G is a Lie groupoid. So if x is in G0, then I call Gx as minus 1 of x, which I just defined, and Gx R minus 1 of x. These two are submanifolds because S and R are submersions. So these are submanifolds. I have left multiplication by gamma. So if gamma is an element in the groupoid, then I have left multiplication, which goes from G S of gamma so this is, so here it would have been useful to actually have notes. So this is left multiplication by gamma. I could also define right multiplication, which is, so this is well defined because the range of this, for this to be well defined, S of this has to be R of this. So this is well defined on this set, and it maps to this set. And it's a diffeomorphism, because its inverse is just left multiplication by gamma. And I have right multiplication, which goes the other way around. So these are diffeomorphisms. Using this, I can identify the tangent space at a point. So just like for Lie groups, I can identify the tangent space of, say, G. So I can identify the tangent space of Gx by R star of kernel of dr. R star of kernel of ds. And the tangent space of Gx by S star of kernel of dr. The pullback of the, here I didn't say, but so this is, yeah, I actually have to say this. So I will write it fast. So this is T at R of gamma. R of, so T gamma is R of gamma, and this is S of gamma. Now it's good. It's really useful to have notes when doing those things, but I'm too lazy to actually write them. This is, so far, this is good. So now I can define my favorite vector bundle. So like before with smooth functions, if you remember, I don't, but if you remember the first course, we had this C infinity of M gamma half and C minus infinity, which was extremely nice. It was extremely nice to look at functions with values in this vector bundle. So now I also have a favorite vector bundle for Lie groupoids, which is omega half of G, which is omega half of the kernel of ds tensor omega half of the kernel of dr. And now I like this vector bundle so much that I will write C infinity of G gamma half to be sections of this. Now, thanks to this, now I can define the convolution. So let f and g to be C infinity functions with compact support on G and omega half. So I can define the convolution by this formula. F of f star g of gamma would be equal to, so I will define a convolution which goes from C infinity functions compact support to C infinity functions with compact support. So it's defined this way, so the convolution will be the integral gamma 1, gamma 2 is equal to gamma on this set, f of gamma 1, g of gamma 2. So what this means, so I'm integrating over this set. I can look at it as the integral of, say, g s of gamma, and this would parameterize gamma 2, and so this is f of gamma 2 inverse g of gamma 2, g of gamma, and then I'm integrating against the gamma 2. Okay. And so what happens here is that the function f and the functions g are sections of this vector bundle. And so the product here will be half density. So it's in kernel ds. So it's half kernel of ds, tensor, half. So I have okay. So what is this product? Where does it live? So g of gamma 2 is a section of this. So I have half density of kernel ds here and half density of kernel dr. So kernel dr, half density, and the half density with kernel ds. And here I have the same thing. I can reorganize these using these isomorphisms and these things, so that this thing becomes an element in, becomes half density in kernel. So half density of g at gamma. So what I want the value of the integral to be also a half density, tensor 1 density of the tangent space of this, so kernel ds. This is the same thing. And so I can integrate this because this is a submersion. So I'm integrating on a smooth manifold, and so I have 1 density on the tangent space of this space, and so I can integrate it, and it becomes a section of this vector bond. So I have a map, I have a convolution map. I have notes, but I can look at them. I can look at them, but I consider this to be cheating. So anyway, so I have this convolution, and this becomes associative algebra. And in the example, so what we care about is that if G is M cross M, the groupoid from before, then the convolution of x and z is the integral over y f of x and y g of y and z. Okay. It's also a star algebra because if f is here. Then I can define f star to be this. The reason we define it by this formula is that if I take the adjoint of f as an operator on L2, then it will be represented by f star given by this kernel. So this is the correct star map. So we constructed a convolution which does what we expect on M cross M. The other example which we could give is E, so the vector bundle. In this case, the convolution would be fiber-wise convolution on the fiber. So f star g on an element E would be the integral over, so E is a fiber over x. So it's pi of E is x. So it would be the integral over the fiber, f of E minus v of E prime, say, g of E prime. And I'm integrating over the fiber. So this is a commutative convolution on vector bundles. So this gives you the difference. So here, for example, the convolution would be commutative because the group is commutative. But here the convolution would obviously be non-commutative. Okay. Yep. So the only theorem which I really need for the moment is existence of approximate identity. So theorem, I can find Fn so a sequence. I can find a sequence in C infinity C of G and omega half such that Fn star F converges to F, F star Fn converges to F for all F in C infinity C of G and omega half. And here the convergence is in the topology of C infinity C of G omega half. Okay, so I can find an approximate identity. And the Fn is the construction is the same as in the Euclidean case for Rn. You just take this type of exponential functions near the space of objects. So now that I define C infinity functions, I want to define distributions. Okay. So I want to define this space. Now here, a crucial difference in the way we think of things is important to mention. So usually, G is a smooth manifold. So if I have, so I could define distributions on G to be the dual of C infinity functions on G. And that would work. And I could make it to be with half densities. But I don't want to think of distributions here on G as dual of C infinity functions. That's not how I will use them. That's almost never how I will use them. And instead, how I will use them is that they are things which allow me to take convolution with. What I really care about, the reason why I use group widths is that I care about convolution. And so I don't really care about all distributions. I only care about some special class of distributions, those which I can take convolution with. And I don't care about the fact that they are distributions. So I will redefine distributions in a way which highlights why I want to use them and how I use them. So I will define this space. I will explain in a moment why the R and S. So this would be its set of two linear maps. So an element here consists of two linear maps. Actually, you don't need them to be linear. You can just suppose that they are functions. So C linear maps, which are, one of them is convolution to the left, which takes C infinity functions. It gives me C infinity functions. And one of them is convolution to the right, which does the same thing. And the main property I ask for is that for every f and g in C infinity C, g and omega half, if I take convolution to the left and to the right, that doesn't matter how I do it. So this is my space. So it's multipliers of this algebra in simple words. Now, theorem. So I suppose that they are linear. I didn't need to suppose this. I didn't suppose that they are continuous with respect to the topology, the natural topology. This is topological, locally convex topological, not locally, yes, locally convex topological vector space. And so this is also locally convex. So theorem, U star and star U are continuous. The proof, extremely easy. The closed, again, my favorite theorem, the closed graph theorem, together with this factor. Because U star F, for example, if I want to do this one. So U star F, I write it as the limit as n goes to infinity of Fn star U star F. So this is true because U star F is a smooth function with compact support. Now I flip by this condition. So I write it as the limit as n goes to infinity of Fn star U star F. So now my operator, U star F, is the limit of these operators, which are convolution by smooth functions with compact support. Convolution by smooth function with compact support is continuous. And so the uniform boundness principle would tell me that the limit is also continuous. And I didn't even need to check linear. So here, I could just say maps. And it would also follow because of this. So, and you do the same thing with F star U. And so this explains how I want to use group weights, things which take convolution left and right. Now we can look at this example to see what we are doing. Before I forget this, technically the distributions I define here are distributions with proper support, because I asked them to map C infinity with compact support to C infinity with compact support. I could, of course, have removed compact support from here, and then that would give me distributions without proper support. I won't use them, so I won't discuss it. So in this case, in M cross M, if I start with an arbitrary distribution on M cross M with values in omega, then Schwarz kernel theorem tells me that convolution to the right is well defined. It takes C infinity functions on M. So if I have a function, then I can define this distribution. But this is usually a distribution. This is not a function. If I start with any distribution in M cross M, Schwarz kernel theorem tells us that continuous linear maps like this are the distributions on M cross M. And so this condition, R and S, is that I don't consider all distributions on M cross M. I only consider these such that the convolution to the right takes a C infinity function and gives me a C infinity function. So U is in C minus infinity Rn S of M cross M omega half if U star F is in C infinity for all F in C infinity and F star U is also in C infinity. So it takes convolution left and right, gives me C infinity function. They have a name in the theory of distributions, but I forgot it. These distributions. Yes?
So it is equivalent to us that U as a map as a function of X is like a smooth map.
So it's yes, so it's equivalent to saying that U it's equivalent to saying that R star of, so this is the way Andrew-Ladakis and Skondalis do it. R star of U is, and S star of FU is in C infinity for all Fm, for all F in C infinity of M cross M. Here this means a push forward in the sense of distributions. But at the end of the day, all I care about is that when I take convolution right, take convolution left, they give me C infinity functions. And I really, that's the only thing I care about, to the point that I will define them to be the things which do that. Okay? So I don't need this theorem. I can now, so now the goal is to give some examples. Of course, you could, just like the space of distributions, we can equip this space with a topology like UN converges to U if for every F, UN star F converges to U star F, left and right. I don't think I will use this. So examples. So I'll give 3 examples which is the only examples I will use. So the first ones are the trivial ones. C infinity is obviously a subset of C minus infinity. That's obvious. The second one, which is much more interesting, is that C infinity of G0. These complex values, there is no bundles, it's complex valued functions. These are also distributions. And the way we do it is this. So, so if F here, then I will define a distribution which I will denote by F Dirac delta of G0. Of course, the notation is motivated by the fact that if G is a smooth manifold, this is F Dirac delta G0. So it's as a distribution, its convolution to the left, it just multiplies by F R G. This is so F is a function on G0, so F circle R is now a function on G. So you just multiply to the left by this function. And the other way around, you do the same thing. G star F, this would be G F circle S. You multiply by functions. And you can check that this has this property. Now I will give the third examples. Yes.
And you multiply by this function.
So you multiply a function on E by f. Yes. And remark, of course, if I take f to be 1, that would, if I take f to be 1, that would give me the identity element in this. So this is an identity algebra. So this is a star algebra. In an obvious way, U star V star F is by definition U star V star F. And the same thing. I know those things are silly. I really like them. So you have to live with them. So it's an algebra in the obvious way. You just compose the maps. This is an algebra if you want to be star. So U star star F. There's only one way to define it, which is U. So you define it as F star star U all star. So you flip 2 times. And the other way around is the same thing. So it's a star algebra in a very obvious way, and it's.
There are two, I'm confused. There are 2 stars. I understand that they're different, that they're defining.
They are the same. They are the same star.
There are too many stars.
There is a convolution and a joint.
Yes, there's convolution.
A joint. So I start with a function f, which is C infinity. I take its adjoint and take convolution with U left. That gives me a smooth function.
I mean, the adjoint is what, f of g minus 1
Yes.
or something more.
Yes.
Complicated. Yeah, okay.
So this is a smooth function. I take its convolution with U left.
And it's a function again.
It's a function again, and then you take the joint again. So there's only one way to do it, because if U was a function, this identity will have to be satisfied.
The thing is that when you take gamma inverse, this reverses the product, the convolution product. That's the product.
That's fine. It's the same thing if in the case of M cos M, it's the same thing. It's the same thing as doing this. If I start with a distribution, then I define a distribution by this formula. Then, of course, I have to interrupt it. So now I want the third type of examples which I care about, which come from left and right invariant vector fields on Lie groupoids, which are a canonical extension of the corresponding theory for Lie groups. So I start with kernel of ds. So I had this vector bundle, and this lives on G. Now I will define the Lie algebroid of a groupoid to be the kernel of ds restricted to G0. Okay. I could have also used kernel of dr. That's a convention. It's the same as when people do Lie groups. They choose left or right. They define the Lie algebra as either left invariant or right invariant. When I do ker ds, it's the same as if I define the Lie algebra as right invariant vector fields. So my convention here follows right invariant. So this is now a vector bundle on this. And my goal is to define a map from C infinity of G, so sections of this vector bundle to distributions. Which you can think of, so in the case of Lie groups, this would be the Lie algebra. And so this would be just an element in the Lie algebra. And you can think of it as I start with an element in the Lie algebra and take it as a vector field on the group. And so in particular, it's a differential operator, so it maps the infinity function.
You mean C minus infinity RS?
RS. Yeah, I might forget RS, but I will never use C minus infinity without RS. So, thank you. So now I want to do this. So I could actually do it here. So I have a proposition. So I can define as two sections x. So start with, so let x be a section of G0 A of G. So I will define two sections, XL, which is in C infinity of G kernel dr, XR, which is in C infinity of G kernel ds. Yeah, I can't do it. I have to cheat. So they are defined by, so XR of gamma. This is the same as saying the right invariant and left invariant vector field on a Lie group, but on a Lie group way. So XR of gamma is dr gamma of x of R gamma. And XL of gamma is so I define this vector field XR, and it has this property, the main property XR is this so there's too many R's, but it's so this equation is just saying that the vector field is right invariant. It's the same equation that you have on Lie groups. And you will also have a similar equation with XL. XL is the left invariant vector field. And now I can define, so if X is always a section here, I can define X, an element in C minus infinity. I will always denote it with X of G to be defined this way. X star F to be XR of F, and F star X to be XL of F. So it's if this was a Lie group, then it's the same as saying that a vector field defines a right and left invariant differential operator. And so I can take convolution to the left by applying the right invariant and convolution to the left by taking the left invariant vector field. Okay, and this defines an element here.
You can also consider an element of the Lie algebra as a distribution with support the identity.
Yes, yes. So this is the same thing as saying that an element of this, an element here, defines a distribution supported at the identity, which actually derivates.
But there is a notion of supported distributions, and but you
Yes. I mean, they are subsets of actual usual.
they're like distributions.
They are this. They are distributions. So why I do this? So okay, so I can explain. So these are distributions, and so you can treat them just like distributions. The main problem is that all of what will appear today are actual Lie groupoids. Next week, I will have something which is not really a Lie groupoid. And so instead of asking, okay, but what is a distribution on something which is not really a Lie groupoid, I'll never use the fact that they are distributions, so that when I go to the more general case, I don't even have to think about the question. Also, the fact that they are distributions doesn't particularly help me, because the way I think of these things is again as something which convolutes left and right. I will never use the fact that they are dual to C infinity functions. I really don't want to think of them this way. So now I can describe how to define classical pseudo-differential operators using groupoids. This is a point of view given by the Valence-Kondalis. And then, so these are classical pseudo-differential operators. I'll construct the groupoids that we need. And then we can do it for classical pseudo-differential operators. And then next week, we construct the groupoids that we need for our pseudo-differential operators. And so then we define the pseudo-differential operators that we need. Okay. So the groupoids that I need is the following. So example. So M is again a smooth manifold. We can define a groupoid, which we call Tm, which is called Conness tangent groupoid. So its space of objects is easy. Its space of morphisms are this. And I will first describe the algebraic structure because it's easier. And then I will describe the smooth structure on this. So S. No, yeah. So the source map takes X and Y. So the algebraic structure, I can describe it in a very simple terms. Here there is a parameter space which is R+. So it's a disjoint union, algebraically, of M cross M the groupoid that we constructed, and that 0 of the groupoid which was the tangent bundle. It's just disjoint union of these things on a parameter space. So x, y, and t, I think of it's, if there was no t, then the example from before, that was y. So now I just add t. I think of t as a parameter. And so an R of x, y, and t, again, x and t is a parameter. The inverse of x, y, and t is y, x, and t. Now this is for t non-zero. So all of this is for t non-zero. What happens at t0? So S of, say, v, x, and 0. V is that element in the tangent space. Then this would be x and 0. So again, if I didn't have 0, then the source for the tangent bundle would be just x. So just x and 0. And R of v, x, and 0 is again x and 0. And the inverse of v, x, and 0 is minus v, x, and 0. And then the product is also given by a very similar formula. So x, y, and t, y, z, and t. So again, if there is no t, then it's x and z. I put t, so it's x, z, and t. I think of it as a parameter, and the other way, it's also the same thing. So that describes my groupoid structure. It's called Condes tangent groupoid because he constructed this in. I'm very bad with citations, but I try to do my best. So he constructed this in the 80s to give a proof of Atiyah's single index formula. Now I need to put, so here I define the algebraic structure, and it's a groupoid because it's just a joint union of groupoids. Now I need to put a groupoid structure. So smooth structure. So here it's obvious, it's just a product of two manifold. So I just need to put a smooth manifold structure on this thing. So I can define it using charts, or I can define it the more elegant way. So I have two maps. I have this map from Tm to m cross r plus, which sends x, y, and t to x, y, and t, v, x, and 0 to x, x, and 0. And the other is that if f is some c infinity function on M such that, if I have a c infinity function on M, then I can define a function which we call the deformation to the normal cone, which is a map from Tm. So this is a complex valued function. So this would be a complex valued function, which takes x, y, and t, and gives me f of x minus f of y over t, and v, x, and 0 would give me df x v. And then, so the topology is a weak topology generated by all of these things. A sequence converges if and only if for this function it converges, and for all such functions, dnc of f is a weak topology which makes all of this continuous. And the smooth structure, it's also the same thing. There is a unique smooth structure which makes all of these things smooth. So this is a special case of a construction known as a deformation to the normal cone construction. You can construct charts for it, but it's really of no interest, so I will not use that. Okay. The main interest here in this groupoid is that when M say at t is equal to 1, so here I have M cross M, okay? Then this groupoid is just the pair groupoid, which comes from the convolution on L2 of M. But when t is equal to 0, it's the groupoid for Tm, the tangent bundle. And so this, first, it creates a sort of a homotopy between these two structures, which is non-commutative at t equal 1 at t and commutative at t equal to 0. And that's the starting point of Connes' proof of a T-single index theorem. But the way we will use it, that's really the crucial way, is that by starting, that's the work of the Barnes-Kondalis, is that by starting with C-infinity functions on this thing, we can construct pseudo-differential operators. And the advantage is that I can relate the principal symbol to this 0 part. So it's a way to construct the principals, to pseudo-differential operators with the principal symbol already given. Yeah. I will also remark that I used here R+, but of course I could use R or R, but what I need is R+. Okay, so one last thing I need is that for any lambda and R plus star, I have groupoid automorphisms, Lie groupoid automorphisms. I didn't define what these are, but it's what you would expect, diffeomorphisms, which are also automorphisms of categories. And so these are defined by alpha lambda of x, y, and t to be x, y, t over lambda, and alpha lambda of x, y, of v, x, and 0 to be lambda v, x, and 0. So the fact that this action exists, or at least it's very easy to see that it's a groupoid automorphism. That's direct to check. It's also very easy to see that it's a smooth diffeomorphism because it's its own inverse. So you just need to show that it's smooth. And it's smooth because it keeps this map smooth, and here it also keeps this map smooth. It becomes just multiplication by lambda. Okay. So the fact that it's smooth is also trivial to prove. So now we can define our pseudo-differential operators. So pseudo-differential operators are distribution on M cross M itself. I will start by distributions here, and then I will restrict them to M cross M at 1. Okay, so we have definition. So if K, I'll write in C for the moment, and then we'll discuss this. But if K is in C, Then we'll define pseudo-differential operators if k is in R. Then we'll define this pseudo-differential operators on this thing to be the set of integrals from 0 to 1 alpha lambda of f d lambda over lambda 1 plus k. F is in C infinity C of Tn. Now, so the first thing, this is correct, this is correct, this is fine if k is negative, and really not fine if k is positive. Why? So what is this integral means? So I want to define this as a distribution on my space. So I just need to know how to take convolution. So if G here this distribution, this integral, if I call it U, then U star G, I define it as the integral from 0 to 1 alpha lambda of f star G d lambda over lambda 1 plus k. Okay, and of course I do the other thing the other way around. Now, I need this integral to converge in the space C infinity C of Tm omega half. If I want this to define a distribution, I need this integral to converge in this topological vector space. Okay? Now, there is an obvious problem, which is that if this was 1, that integral already blows up when k is positive at k equal to 0. Okay, I think so. I learned this a few years ago. So when k is positive, this thing blows up, and so that's why I need k is negative. Now, when k is negative, it doesn't blow up, and the observation, so the observation here is the following. So this action was defined for R plus star. So a priori, there is no alpha 0 of f. And so the observation is that this thing, which say I have f and g are fixed. So this thing, I think of it as a map from R plus a star to C infinity C of Tm omega half. So the observation is that this extends by smoothness to lambda equal to 0. So extends smoothly to R plus. And so since it extends, it also everything I'm saying also works if G was in the other way around. And so since it extends, this means that I have an element which I call the limit. So I can define alpha 0 of f to be the limit as lambda goes to 0 plus alpha lambda of f. And this limit would exist in the sense of distribution. So this would exist in C minus infinity R and S of Tm and omega half. And so this explains why this integral converges. This is a continuous function in a locally convex topological, complete locally convex topological vector space, so I can integrate. Okay. This thing is just Dirac. Times some normalized by the integral of f. But it's essentially a Dirac distribution on the identity, on the space of objects here. So on the diagonal of M. So this explains why the integral exists. Okay. And so this gives you a distribution on this space. Okay. Now, I need, so I want to erase, yeah. So now I have two problems which are orthogonal to each other. I will solve one of them, and maybe I will not have time. Hopefully I will not have time to solve the other one, so I'm good. So the first one is that I need to tell you what happens if k is positive. And the second one is that I need to tell you how to go from these to pseudo-differential operators on the manifold itself. So I can tell you the second problem. This is easy. So in general, if G is a Lie groupoid and A is a subset, is a submanifold, A is called saturated if for every gamma in G, if S of gamma is in A, S of gamma is in A is equivalent to saying that R of gamma is in A. The source is in A is equivalent to saying that the range is in A. The idea here is that your groupoid G becomes a disjoint union of G restricted to A union G restricted to A complement. Things which have source in A and things which have source in A complement. Of course, this is disjoint union algebraically. Smoothly, you would not have this. It's a disjoint union as a groupoid, algebraic, not as a Lie groupoid, which is what we had from before. So the example, so the typical example is M cross 1 inside M cross R plus is saturated in Tm, which is just saying that what I said from before, Tm is just disjoint union of groupoids. Just a fancy way of doing it. And so the general thing is that if I have this saturated, then I can take the restriction, which is the set of gamma in G, such that S of gamma is in A, which is also equivalent to saying that R of gamma is in A. This is a Lie groupoid. And we always have a restriction map from C minus infinity of G omega half to C minus infinity of G restricted to A of omega half. And the construction is very simple. You start with U, RS. What? This time it's important. So you start with U, and then you start with a function which is smooth just on G cross GA. Here I need A to be closed. For this part, I didn't need A to be closed. Just saturated makes sense for any A, but here I need A to be closed. So C infinity of G restricted to A, and then I take any extension of F to the whole G, and then take U star G, and then I restrict it to A, to GA, where G is an extension. And this doesn't depend on the extension because A is saturated. And because U is in RS. Because of the condition that we had in the definition of U. You can check that this is well defined. So in fancy words, so all of this to say, I also want to erase this.
It's locally closed to it.
Do you always need it to be closed?
Because you extend this here. If you have something with convex support to make it, it's locally closed.
Yeah, you probably are right. I don't need it to be locally closed. For this, I probably should check my notes. But anyway. So this means, just to simplify everything we said, we start with some C infinity function here. So it's a C infinity function. Remember, this space is written like this. And so this integral when you restrict it to, so in the case of the tangent, groupoid, M cross 1 was the saturated set, GA, elements which have source in A, that's M cross 1. So when you restrict it to M cross 1, this is the same as saying you take the integral from 0 to 1 f of x lambda d lambda over lambda 1 plus k. So all of this to say that we start with a C infinity function on M cross M. So here I don't need really all of R plus star. I could just work with 0, 1. But so I start with a function on this part, and then I ask this integral to converge. And I want it to be a pseudo-differential operator. So these are properties. For this to be a pseudo-differential operator, classical pseudo-differential operators, you ask for properties of asymptotic expansion of this kernel near the diagonal. And so the trick of what's happening here is that this integral transfers all of the conditions that you are asked for here to the conditions that F admits a smooth extension to Tm, which is also a condition of asymptotic expansion. Now asymptotic expansion just becomes Taylor series, but asymptotic expansion of F near the diagonal. Okay? Now, the advantage of having this thing before I do the restriction. So I had this. This was something in C minus infinity. So C. So this is a distribution here, d lambda. So this was a distribution here. And so I could also restrict it to other saturated subsets. And so I have another saturated subset because my groupoid was a disjoint union. I could also restrict it to M cross T, but that makes no interest. It's just dilation of what's happening. But I can restrict it to the set which comes from A is equal to M cross 0, and the corresponding GA would be Tm cross 0. And then the restriction at 0 would become the principal symbol. So I restrict it to Tm cross 0, and this is the principal symbol. So this approach gives me pseudo-differential operators, but they come also with a homotopy, if you want, between the operator and its symbol. The homotopy would be the restriction of this at M cross T. Okay, and this is the starting. This is really all of the main point in Kahn's proof of Atiyah-Singer index theorem, and it will also be the main point in for our proof of these three properties F 5 prime and the other ones. Once we construct the correct analog of this in our case. Okay. So next week I will discuss the problem of what is happens when k is positive, which I kept hidden for now. And then I will explain what advantages the fact that this was a groupoid, Lie groupoid bring to the pseudo-differential operator. All of what I will say is known. It can be proved using other methods, but I will explain what are the quick advantages that this brings. And then the whole point would be to generalize this space to a space which now involves Hörmann-Dars condition. And then we redo the exact same thing. We redo the same formula. We will have the same observations that alpha lambda of f as lambda goes to 0 converges. So these integrals give me distributions. And so they give me a homotopy between pseudo-differential operators and their symbols. And from this, I'll get everything that I want. So I'll stop here.